Welcome everyone to section 3.3, which introduces a new rule for derivatives. So today we are learning about the chain rule. Alright, so we need the chain rule when taking the derivative of a composition of functions. Alright, so we'll jump right into it. Say that we have y is equal to f of g of x. Okay, so this is a composition of functions, right? In this case, we're going to say that g of x is the inside function, okay? And I'll say g is the inside function and f is the outside function. Alright, right? Because g is inside of f in this instance, okay? So, if we have f of g of x, then our derivative with respect to x of f of g of x, well, this is going to be, first we're going to take the derivative of f, so we'll use function notation, so f prime, okay, but leave the inside alone. Alright, so leave inside alone. Just take derivative of outside. Okay, then we're going to multiply that by the derivative of the inside. Alright, if we want to see this in our Leibniz notation, so I'll give us a little bit more space to see this in Leibniz notation. So if we have y is a function of z, and z is this function of t, then dy dt is equal to dy dz times dz dt. Alright, and I know it's really hard to see these rules and get this immediately start understanding this, but that's why we're going to now implement some examples. Alright, so a gives us y is equal to the natural log of q squared plus 1. Alright, so let's go ahead and write down a few things that we know. Alright, so we know. What do we know about natural logs? Well, if we wanted to take the derivative of a natural log, if we just had ln of x, we learned a little bit ago that this is just 1 over x, right? Okay, so we know this derivative. In this case, we're going to need to use the chain rule. Alright, chain rule, which is the rule we just wrote down. So we need to identify the inside and outside functions. Let's do the inside function first. These are usually easier to find, especially if we have parentheses. Those are really helpful in helping identify our inside function. So we have parentheses here, and to me it looks like q squared plus 1 is our inside function. And we have to take everything, okay? We can't just pick the q squared or the 1. We have to pick everything that's inside our other function, which is going to be our natural log, but I'm getting ahead of myself. Alright, so the inside function we've determined that this is q squared plus 1. All right, so then our outside function, well, what is the q squared plus 1 inside of? In this case, it's our natural log. Okay, so our outside function is the natural log, and I'm just going to leave these blank parentheses, the natural log of something, but it's just the natural log that we care about, right? So if we're trying to calculate dy dq in this case, this is going to be the derivative with respect to q of our natural log of q squared plus 1. So now we need to start implementing our chain rule. Okay, so our chain rule said it was the derivative of the outside, and leave the inside alone, times the derivative of the inside, right? Okay, so we determined our outside function is the natural log, which we know our derivative of the natural log is 1 over something. Well, let's go back and look up at our chain rule here. Okay, we leave the inside alone. We leave the inside alone. So that means we need to leave g of x as is inside our function. Okay, so our 1 over something, that something, is going to be our g of x. So this will be the q squared plus 1. Okay, but we're not done yet. We need to multiply this by the derivative of the inside. So in order to avoid doing too many things at one time, I'm going to go ahead and write it like this. Alright, so this is our derivative of outside, okay, and I'll say evaluated at inside function. So evaluated at x is equal to 2. In this case, evaluated at q is our q squared plus 1. Okay? And then times the derivative of our inside function. So we have 1 over q squared plus 1 times the derivative of q squared plus 1. Well, we could go ahead and split this up into several different steps, but I think we're ready to go ahead and look at this one and see it should just be 2 times q, right? So I'll go ahead and tell you the intermediate steps there. We could split the sum, so it's 2 different derivatives. The derivative of q squared, that's a power rule. So we bring down the exponent and then subtract 1 from the exponent. And then the derivative of 1, well, that's a constant, so our derivative is 0. So that's how we get 2q. Alright, and then if we want to go ahead and drop these brackets, we end up with 2q over q squared plus 1. And that is our final answer. Okay? So the chain rule is a little bit tricky to get started, but that's why we have so many examples to make sure we can understand this, alright? Let's go ahead and look at our second example, so part B, where we have g of x is equal to e raised to the negative x squared. Alright, in this case, we don't have any parentheses, so it might not be super intuitive to know where do we have the inside function and where do we have the outside function. Alright, so, but we still need to identify them. So we have the inside function and the outside function. Because we're going to need to use multiple rules here, right? We notice that we're definitely going to need an exponential rule. All right, and because this is in the section that talks about the chain rule, we should need the chain rule too. All right, and then the inside and outside functions associated with the chain rule. Okay, so like I said, might not be immediate to find the inside function here, but our inside function is actually going to be our negative x squared. So it's what we have in our exponent. Okay? And then our outside function is actually going to be e to some power, right? Some power of having to do with x, obviously, or else it would just be a constant, right? If it was e squared, that's just a constant. But here we have our outside function is e to some power, okay? So, if we want to find g prime of x, we need the derivative with respect to x of e to the negative x squared. So, this is our derivative of our outside function. Well, our outside function is e to some power. And we know that the derivative of e to some power is itself, right? So, e, that some power, is the original inside function. So we have e to the negative x squared. So that's the derivative of the outside function, and then we're going to plug our inside function into it, times the derivative of our inside function. So the derivative of negative x squared. So we have e to the negative x squared times our derivative. Well, our derivative of negative x squared, pull the 2 down, and so it's negative 2x. If we go ahead and clean this up a bit, we end up with negative 2x over e to the x squared. And this is our final answer for our derivative. All right. Let's keep going to part C, where we have y is equal to 4t squared plus 1, all raised to the 7th power. Alright, so again we're going to need the chain rule. We're also going to need some power rules. And then we need to determine our inside and outside functions. Inside function, outside function. Alright, here we have some parentheses. So our inside function is all of this in here. Our inside function is going to be 4t squared plus 1. And our outside function, well, what are we doing to the inside function? We're raising it to the 7th. Alright, so this is our something raised to the 7th, right? Okay, so if we want dy dt, that's our derivative with respect to t of our 4t squared plus 1 raised to the 7th. So first we need our derivative of the outside function. So this is just a power rule. We bring down the 7, and then we raise it to 7 minus 1, which is 6, right? That's a power rule. But then we leave the inside function alone. The inside function is the same. Okay, so again, this is our derivative of the outside evaluated at the inside, so you plug the inside back in, times then our derivative of our inside function. Okay, and you're not done with taking this derivative until you've finally taken that derivative of the inside function as well. All right, so we have this 7 times 4t squared plus 1 raised to the 6th power times, well, we have the derivative of 4t squared plus 1. Again, we could do this in several steps, or we could see that the derivative of 1 is 0, and then the derivative of 4t squared will bring down the 2, and then that's going to get multiplied by the 4, so we'll have 8t. Okay? So we can clean this up just by dropping these brackets and multiplying through. So 7 times 8t, that gives us 56t times 4t squared plus 1 raised to the 6th power. And that's our final answer for this problem. All right. Next, we're going to look at part D, and this is a lot of pieces to it, okay? So we're going to break this down as much as possible so that it's easier to chew, right? Okay, so we want dp dx, which is going to be the derivative with respect to x of everything on the right-hand side. So 2e to the x squared plus 7 minus 5 natural log of 2x minus 1. All right? And I know in the last few examples we kind of left a little bit of the simplification alone, and we did a few steps in our heads. But in this case, there's so many pieces happening that we're going to want to do all of the steps and write them all out. Okay? So the first thing I want to do is split over this difference, split over the subtraction. So we're going to have the derivative with respect to x of our 2e to the x squared plus 7 minus the derivative with respect to x of 5 times the natural log of 2x minus 1. All right. Then for both of these, we can use our constant multiple rule. So the 2 comes out front. We have the derivative of e to the x squared plus 7 minus 5 times the derivative of the natural log of 2x minus 1. Alright, so now that we've broken this down and simplified as much as possible, it's finally time for us to start evaluating these derivatives. Alright, so we're going to need the chain rule, alright, because immediately maybe we see this natural log has an inside function going on, right? So we're going to need the chain rule. We also have an e to something, so we're going to need an exponential rule. Okay. And most likely a power rule in there too. And we're going to need to determine these inside and outside functions, but for both of these split derivatives. Alright, so let's go ahead and focus on one at a time. So let's focus on this one here first. Alright, specifically just what's inside here. Okay, so let's find the inside and outside functions. So we have e raised to the x squared plus 7. Earlier we had an e raised to the negative x squared, and our inside function was the exponent. It was our negative x squared. So if we think in a similar manner, our exponent is x squared plus 7. So our inside function is going to be x squared plus 7. Okay? Next, our outside function. Well, our outside function is just our base e raised to our inside function, right? So it's our e raised to something, okay? And if we want to actually label these instead of having some spaces around, if I say this is g of x, and I say this is f evaluated at g of x, then this is e raised to the g of x, okay? If that helps you. So we need our derivative of e to the x squared plus 7. I'm going to go ahead and move this over more. There we go. So we need our derivative of the outside function. All right. A derivative of e to something is just e to something, right? And g of x is our x squared plus 7. Then we need to multiply that times our derivative of the inside function, which we determined was x squared plus 7. So we have e to the x squared plus 7 multiplied by, well, the derivative of 7 is 0, and the derivative of x squared is just 2x. So we end up with 2xe to the x squared plus 7. All right, and this is just a piece of the puzzle. I'm going to go ahead and bring this down here. Okay. Ooh, wow, I need so much more space. So we had 2 times the derivative that we just calculated. So 2xe to the x squared plus 7. All right, and then we had minus 5 times this other derivative. So I'm going to go ahead over here, and let's go ahead and find the inside and outside functions for this derivative. All right, so our inside function is whatever is inside our parentheses in this case. So our inside function, this is our 2x minus 1. All right, if you want to call it g of x, go ahead. So then our outside function, well, this is our natural log. So if we call it f of g of x, it's going to be our natural log evaluated at g of x. All right, so if we have the derivative with respect to x of the natural log of 2x minus 1, our very first example today had to do with this. We know the derivative of the natural log is 1 over whatever's on the inside, right? So we have 1 over whatever's on the inside, our 2x minus 1, times the derivative of the inside, 2x minus 1. So we end up with 1 over 2x minus 1. The derivative of 1 is 0. The derivative of 2x is just 2. All right, so we end up with 2 over 2x minus 1. And that is our second piece of the derivative that we've now calculated. But we need to go ahead and plug this into our full equation. All right, so we had 5 times that derivative that we just calculated. So 2 over 2x minus 1. We are so close. I know this is a long problem. All right, but we want to go ahead and clean this up and drop these brackets. So we'll multiply through and end up with 4xe to the x squared plus 7 minus 10 over 2x minus 1, and that is our final answer. All right, so we're going to start back up at the top of this problem and just kind of recap what we did here. So we broke it down and simplified it as much as we could before needing to take the derivative. So that's going to make our derivative calculations as simple as we can get them, okay? Then we noticed we're going to need to use the chain rule twice in two different areas here. We needed to use an exponential rule, also a power rule, okay? So again, to make this easier to go about, we went ahead and looked at one piece at a time. So we looked at the first derivative, and then we looked at the other derivative. I said other instead of second, so we don't get confused here. Okay? So then we had the inside and outside functions, and we went ahead and calculated the derivative using the chain rule, and we did the same thing for the other derivative here. But the whole question was asking for everything put together, so we couldn't just calculate the two derivatives separately. We had to plug them all back in to get our final answer. Alright, so now we're going to move on to example 2, where it asks us to use the given graph to find the following derivative values. Alright, so we're asked to find h prime of 1 if h of x is equal to the composition f of g of x. So here we're given graphs of f of x and g of x. Alright, and we're asked to find h prime of 1. So, by the chain rule, we know that h prime of 1 has to be the derivative of our outside function, which is f, evaluated at our inside function, but instead of saying g of x, we need the value that we are interested in, which is 1. So it's going to be g of 1, and I'm missing my prime. So the derivative of the outside function evaluated at the inside function, which is evaluated at the number that we are interested in, okay, times the derivative of the inside function, again evaluated at the number that we are interested in. Alright, so first things first, let's go ahead and try to figure out what g of 1 is based on our graph. So g of x is our straight diagonal line here. It's the orange line. And looks like we have tick marks only every 2. Okay, so this is 1 right here. So if we want g of 1, we want the value that our line gives us at, which is 7. Alright, so g of 1 gives us 7. So we can go ahead and say that we now have f prime evaluated at 7 times g prime evaluated at 1. So now we need to find f prime of 7 and g prime of 1. So g prime of 1, this is our slope at g of 1, at x is equal to 1. Alright, so again, we need a slope. Well, the first thing that I notice is our slope is negative. Okay, we have a line going down, so we have a negative slope. And then we need to figure out what that slope is. So this is going right, so that gives us 1 over 1, which is 1. Alright, so now we have f prime of 7 times negative 1, and we need to find f prime of 7. Well, that's our slope, where f of where f is equal to 7. So now we need to find f prime of 7. So that is our slope where x is equal to 7 over here for our function f of x. Alright, well that is just a horizontal line. So we know our derivative there is going to be 0. We have a 0 slope on a horizontal line. So we end up getting 0 times -1, which is 0. A little anticlimactic if you ask me. Alright, let's do it again. So part B gives us another one and asks us to find k of 2. This time our composition is g of f of x. So we need k prime of 2. K prime of 2. Again, by the chain rule, our k prime of 2 is going to be the derivative of our outside function, evaluated at the inside function, evaluated at the number that we care about, times the derivative of our inside function, evaluated at the number that we care about. Alright, so first things first, we need f of 2. So let's go back up to our graph. Here is 2, so f of 2 is this point here, which is 4. So we have g prime of 4 times f prime of 2. So f prime of 2 is what is the slope that is happening at x is equal to 2. So here we have a positive slope. We have an increasing line. Alright, so it looks like we go up 1, up 2, over 1, right? This is our 1 line here. This will be 3. Alright, so we went up 2, over 1. That gives us a slope of positive 2. So f prime of 2 is equal to 2. And I didn't write down that f of 2, is equal to 4. Alright, and let's go ahead and find g prime of 4. So we need, when x is equal to 4, over here, what is our derivative say about the slope of this line? Well, we go over 1. We know we're going to be negative. We go over 2, right, because it's between 4 to 6. So we go over 2 and down 2. So we have 2 over 2, which just gives us our 1, right? But of course it's negative. So we have -1. So we end up with -1 times 2. So -2 is our final answer here. Alright, so that's how we can calculate some chain rule derivatives just by using a graph. Now we're going to look at calculating our derivatives using a table. Okay, so we're to use this table below to evaluate the following quantities. So we need h prime of 4, where h is the composition, g of f. Okay, so again, using the chain rule, h prime of 4, this is going to be our derivative of the outside function, evaluated at the inside function, evaluated at the number that we care about, times the derivative of our inside function, evaluated at the number that we care about. Okay? And we need to go get all of these values from our above table. Okay? So we need f of 4. So we'll look at the f of x row, And the 4 column defines that f of 4 is 2. So we need g prime of 2 times, well, what's f prime of 4? So now we need to look at the f prime row, again the 4 column, and we find that f prime of 4, is also 2. So we have g prime of 2 times 2. So we need g prime of 2. So now we look at the g prime row and we find that g prime of 2 is equal to 3. So we end up with 3 times 2, which is 6. And that's it. Okay? We just have one more example using this table. For part B, we would like to find h prime of 2 when h of x is now f of g of x. So in this case, we have our chain rule telling us that this is f prime of g of 2 times g prime of 2. Okay? So g of 2, based on our table, is 3. So we have f prime of 3 times, well, g prime of 2 is also 3, based on our table. Alright, so f prime of 3 times 3. So f prime of 3, our table says 5. Alright, so we end up with 5 times 3, so we get 15. Okay. Of course, we need to do a problem that involves finding the equation of a tangent line, right? So, x minus 4 all to the 7th at x is equal to 5. So remember, we need to find the derivative, evaluate it at the point. Then we need to find our y value and plug our point and our slope into our equation for a line. Alright, so we need h prime of x. So this is our derivative with respect to x of x minus 4 quantity raised to the 7th. This is going to need a chain rule. Okay, so we need chain rule. We're going to go ahead and skip writing the inside and outside functions. See if you can add that part in here. We're just going to go ahead and calculate this chain rule. So the first thing that we need to do is evaluate the outside function. So that's our raised to the 7th power. So we need to bring the 7 down, and we need to subtract 1 from our exponent. So 7 minus 1 is 6. Then we need to evaluate that at our regular inside, x minus 4. And then we need to multiply that by the derivative of the inside, which is x minus 4. Alright, so then we have 7 times x minus 4 to the 6th. The derivative of x minus 4, well, the derivative of minus 4 is 0, and the derivative of x is 1. So that's just 1. So we don't need to write multiplying by 1, right? It's redundant. It wouldn't be wrong if you did, but it's just unnecessary. Okay, so we found our derivative, h prime of x, which we now need to evaluate at x is equal to 5. So h prime 5. That gives us 7 times 5 minus 4 raised to the 6th. Well, 5 minus 4 is 1, so we have 7 times 1 to the 6th. 1 to any power is 1, so we have 7 times 1, which is 7. And we remember that our derivative evaluated at a point is the slope at that point, right? Then we need to find the y value. So we need to plug in our x value to our regular equation. H of 5 is equal to 5 minus 4 to the 7th. Again, 5 minus 4 is 1 to the 7th, so we get 1. So we found our slope, which is 7. We found our point, which is the given x value of 5. And we found the y value is 1. All right, this is our point. So our equation of the line is y minus 1 is equal to 7 times x minus 5. And this is in point-slope form, but if we want it to be in y-intercept form, which is what we might always associate as the equation of the line, we can go ahead and distribute this 7 through and then add 1 to both sides. So we get y is equal to 7x minus 34. And this is our equation of the tangent line. Alright, we just have one more example here, example 5. So a company called Office Min finds that they have a revenue for their printers that follows this function R of Q is equal to the natural log of 1 plus 500 Q squared. So we're supposed to calculate the marginal revenue and interpret R prime of 10. So first we need to remember that marginal revenue just means the derivative of the revenue, right? So let's go ahead and calculate the derivative. So we need R prime of Q, which is the derivative with respect to Q of our natural log of 1 plus 500 Q squared. Okay? So we're going to need to use the chain rule, where we know the derivative of the natural log is the 1 over the inside function. So 1 over our inside function, which is 1 plus 500 Q squared, and then multiply that by the derivative of the inside function. Okay, so we have 1 over 1 plus 500 Q squared times, well, the derivative of 1 is 0, and the derivative of 500 Q squared, well, we need to bring the 2 down, so we'd have 2 times 500, so we have 1,000 Q. Alright, so we end up with 1,000 Q over 1 plus 500 Q squared, and this is our marginal revenue. Finally, we were asked to interpret R prime of 10. Alright, so let's come over here. R prime of 10, oops, there we go. Well, that's 1,000 times 10 over 1 plus 500 times 10 squared. Alright, so a calculator is going to tell us that this is 0.19, alright, which we could go ahead and round up to 0.2. And what does this tell us? So a revenue is usually dollars over quantity, right? Or the number of items. And the derivative tells us our rate of change, right? So our marginal revenue, that's how much our revenue will change by adding one more item. So our interpretation says after making 10 printers, that looks like an L. 10 printers, that also looks like an L. Anyways, after making 10 printers, revenue will increase, because it's positive, will increase by $0.2 for each printer. Okay, which would be 20 cents. Alright, so that wraps up 3.3. Don't forget to take the comprehension quiz, and I'll see you in the next lecture.